first lecture in Chapter 16, Waves and Sound. And here is a picture of a pretty big water wave. And we're going to be discussing water waves and the speed of the water and the amplitude of the water and the wavelength of the water and so on. The first thing we want to know, though, is what is a wave? It's a disturbance or variation that transfers energy progressively from point to point in a medium. A good example of that is when a motorboat travels along and leaves a wave behind, energy is transferred from the motorboat to other boats, like this fisherman here out on the lake. Here we're showing transfer of energy. There's a variety of things. The top wave is a transverse wave, and people are standing and sitting, and so we're seeing this wave-like fashion here. This next picture right here is gas molecules being hit by a piston, and you can see the wave traveling along. That's called a longitudinal wave. You have compression points and expansion points all along this gas, and where you can see where they come together, it's a compression point, and then right behind it, it becomes an expansion point, and energy is transferred from one point to another. Sound waves work this way. And then below here we have a rope that's being lifted up and down, and we're sending energy from this point here down to the other point down there, and that's done by a wave. We show this wave here traveling along, and what this is meant to show is that the material, the actual, if this black line is a rope, the rope actually vibrates up and down as the wave passes through. The rope itself does not travel forwards or backwards. It actually just travels up and down, and that's what that red dot is trying to show us, is that parts of the wave actually just travel up and down. So one type of wave we have to know is called a transverse wave. The hand is moving back and forth, up and down, and a S-shaped wave, like a sine curve, is being formed. And you'll see that the particle right there, if you see the hand is moving up and down, the slinky particles are actually literally moving up and down. They don't move forwards or backwards. They just move up and down as the energy transfers from left to right. And we have to know what the characteristics of this transverse wave is. There's four characteristics we have to know. We have to know the wavelength, the amplitude, the crest, or the trough. So you're definitely going to want to write this down in your notebook, all these pieces here. In this pink section, there is a wave, a full wavelength. That uses the variable lambda, an upside down y. The amplitude is measured from this middle line to the trough, or from this middle line up to the crest. It's not the whole distance, it's from this middle line, this equilibrium line. And you'll see here that a crest is the very top point and the trough is the very bottom point. And this black line is when this wave, if this was water, it'd be undisturbed, or a slinky, this would be where it would be if it was undisturbed. Now we're going to look at a longitudinal wave. And a longitudinal wave is a wave where the hand is moving back and forth. You'll see this arrow showing the hand moving back and forth. And you have areas of compression right here, and then behind it you'll have areas of expansion, the stretched region. And so you'll see that this wave, if you look, here's a compression area, and then you have expansion, 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 all in between. So one wavelength would be from one expansion to the next expansion, or one compression to the next compression. Just like previously, it would have been from one trough to the next trough, or from one crest to the next crest. Here is, again, here's a sound wave traveling in a gas tube, and you'll see there's areas of expansion, that's where there's low pressures, and areas of compression, that's areas of high pressures. So sometimes you'll see low and high pressures, expansion, compression. Just depends on, it means the same thing. Low pressure or expansion area, high pressure is a compression area. And you can draw transverse waves to match up to these longitudinal waves. For example, you'll see in a compression area, we've made it a crest. In the expansion areas, we've made a trough. And so wherever you have a expansion, there's a trough. Compression is a crest. They'll call it condensation or rarefaction instead of compression and expansion. The equations we have to look at are this. We have frequency equals 1 over the period. We've talked somewhat about this. but the frequency is the cycles per second, the oscillations. In other words, it's the hertz. Period is the time for one wave to pass through a certain point. That's the time in seconds, and frequency is the number of oscillations per second that occur. So F equals frequency, waves per second or hertz. T is period, which is in seconds. And the second equation is velocity equals distance over time. The distance we're working with is one wavelength. The time we're working with is the time for that one wavelength. So that's distance over time, wavelength over period, which also can be rewritten as, instead of 1 over period like we have right here, we can plug in frequency. So the equation you'll see quite often is velocity equals frequency times wavelength. V is velocity in meters per second, wavelength is in meters. Here's an example of a problem we may come across. It says AM and FM radio waves are transverse waves that consist of electric and magnetic disturbances. These waves travel at a speed of 3 times 10 to the 8th meters per second. A station broadcasts an AM radio wave whose frequency is 1,230 times 10 to the 3rd hertz, which is 1,230 kilohertz on the dial, and an FM radio wave whose frequency is 91.9 times 10 to the 6th hertz, or 91.9 megahertz on the dial. Find the distance between adjacent crests in each wave. Now when they say the distance between adjacent crests, what they're really asking for is the wavelength. We know from one crest to the next crest it's a wave. So pause the video and see if you can calculate the wavelength. Here are the answers. Once you do that, you use the equation velocity equals frequency times wavelength. And you'll notice that the AM radio waves are huge. It's 2.5 football fields long. The FM radio waves are fairly short, 3.26 meters long, which is about 10 feet. So that's why when you go into a tunnel, typically you cannot hear AM radio. AM radio gets cut out because its waves are so long, they cannot fit inside the tunnel. So with this lesson, you want to have known what is a wave, and you also want to know what types of wave there are, longitudinal and transverse. You also want to know our equations for waves as well. Velocity equals frequency times wavelength, and velocity equals wavelength over period, and frequency equals 1 over the period. So those equations also you have to know. And the very last thing I wanted to point out here is the idea of superposition of waves. As two waves come at each other, they actually will go through each other. You'll see on the right-hand side here we have one wave going to the right, but that wave right there goes through. See how that smaller wave keeps going through? And when they're on top of each other, they actually add up. You'll notice that if you watch this dashed line right there, it actually goes through the bigger wave. But when they're on top of each other, they add up. Here you'll notice the top two waves are both traveling to the right, and what we're having here is constructive and destructive interference patterns. When it's flat, you'll see it's right here, it's destructive interference, and then when it gets bigger, it's constructive interference. If you look above how they line up, see right there, a crest and a trough hit each other, so you have destructive interference. Here we have two sine waves going in opposite directions, the top wave to the right, the bottom wave to the left. And you'll see whenever a crest and a trough are lined up, you have destructive interference, and whenever a crest and a crest or a trough and a trough line up, you have constructive interference where it gets bigger. So this concludes the chapter 16.1. This will be chapter 16.1a lesson.